4 in our textbook. It's entitled Reactions in Aqueous Solution. During this chapter where we're going to discuss an alternative to simply solids, liquids, and gases. But what happens when you take those reactants and dissolve them in water? Can you facilitate a chemical reaction by dissolving something in water? Well, a solution is a homogeneous mixture of two or more pure substances. You can think of a glass of salt water where we take some salt and dissolve it in water, or some sugar water. Take sugar and dissolve it in water. Or even a can of soda. If you look at the ingredients on the can of soda, it's likely to begin with carbonated water, and then we see things like fructose, high fructose corn syrup, sucrose, flavors, colors, caffeine, different substances that are all dissolved in that carbonated water. Now, there are two parts to a solution. There is the solvent and there is the solute. The solvent is the substance that does the dissolving, and the solute are the substances being dissolved. So in the case of a glass of salt water, water would be the solvent, salt would be the solute. So you're dissolving solute in solvent. Another way of thinking of this is that the solvent is the substance that is typically present in the greatest amounts. So in a glass of salt water, there's a lot of water and some salt. In a glass of sugar water or Alabama sweet tea, there's a lot of water and, well, there's probably a lot of sugar if it's Alabama sweet tea, but more water than sugar. That's what makes the solvent water and the solute what is being dissolved in water. Now, solutions that have water as the solvent are called aqueous solutions. Well, how do compounds dissolve in water? Well, depending upon the nature of the compound, that's going to dictate how the compound dissolves in water. Ionic compounds, for example, when ionic compounds dissolve in water, they do so by dissociating. The process of dissociating means to break apart into ions when placed in solution. So an ionic compound like sodium chloride, when you place it in water, the sodium cations and the chloride anions that are attracted to one another are going to break apart and spread out into solution. A more appropriate explanation would involve water molecules disrupting those interactions and surrounding each ion so that it can't easily attract another ion. If you have a sodium cation, which is positively charged, and a chloride anion, which is negatively charged, and water molecules not only disrupt that interaction, but then surround each ion, then it's going to limit the availability for those two ions to recombine based on water simply being in the way. These ions are said to have undergone solvation. Molecular compounds, on the other hand, when they dissolve in water, it's not a matter of them breaking apart into ions, but again, it is the particles separating from one another. So in the case of sugar, which is a molecular compound, it has the chemical formula C12H22O11, that is sucrose. That's not going to break apart into ions. Instead, when that dissolves, all of the individual molecules of sucrose are going to spread out into solution. And once again, that takes place by solvation, where the molecules are surrounded by water molecules. And since there are so many more water molecules than solute molecules, then we see separation of the solute molecules from one another. Now, as we discuss aqueous solutions, we need to discuss the concepts of electrolytes and non-electrolytes. An electrolyte is a substance that will dissociate into ions when dissolved in water. A non-electrolyte does not dissociate into ions when placed in water. It may dissolve, but it doesn't dissociate. So what we can glean from this is that most molecular compounds are non-electrolytes. Because again, most molecular compounds are not going to dissociate into ions. There are some that will. We'll discuss those in just a moment. The electrolytes, those substances that do dissociate, break apart into ions when placed in solution. The properties of solutions that contain electrolytes are very interesting. Compounds whose aqueous solutions conduct electricity are known as electrolytes. It is the presence of ions in solution that allows the transport of electric charge that is electricity. Well, some electrolytes will allow for a high level of electrical conductivity and some a poor or a low level of electrical conductivity. What's the difference? Well, we can break down the term electrolyte into two categories. The terms strong and weak refer to electrolytes, and specifically they speak to the extent of dissociation. A strong electrolyte will completely dissociate or completely break apart into ions when placed in water. A weak electrolyte will only partially dissociate. I'll give you an example. Sodium chloride is a strong electrolyte, as you see in the images listed atop the slide. If we run a current through a solution that includes sodium chloride, we will see that the electrolytic solution conducts electricity very well. That's because sodium chloride, when placed in water, will completely dissociate. If you look in a solution for intact sodium chloride, you're not likely to find it. Sodium chloride is going to break apart into Na plus and Cl minus. A weak electrolyte will only partially dissociate. There are some substances that when you place them in water, for every 100 that you place in water, maybe only one of those units will dissociate. That is the case with a weak electrolyte. Acetic acid, the active component in a bottle of vinegar, is a weak electrolyte. If you place acetic acid in water, then only part of it is going to break apart into ions. And a non-electrolyte does not dissociate in water. The images that we see show a strong electrolyte on the right in terms of sodium chloride, pure water, which has nothing dissolved in it, and a non-electrolyte in the form of sucrose or sugar. Here we essentially see the reaction scheme that takes place when a strong electrolyte and a weak electrolyte are placed in water. When a strong electrolyte, such as HCl, also known as hydrochloric acid, is placed in water, it forms an aqueous solution. HCl with AQ in parentheses speaks to hydrochloric acid dissolved in water. Now that will break apart into the component ions H plus and Cl minus. This is an example of a molecular compound that is an electrolyte. Hydrogen and chlorine are both nonmetals, so they combine to form a molecular compound. But this is an example of a molecular compound, one that we're soon going to call an acid, that breaks apart into ions, an H plus and a Cl minus. A weak electrolyte, only partially dissociating, we see the instance of a weak electrolyte in the second equation. The second equation speaks to that of acetic acid. Now, acetic acid dissociates to form H plus and CH3COO minus, that acetate ion, for those of you who are keeping up with your polyatomic ions. Now, you'll notice one difference in the equation for a strong electrolyte's dissociation and a weak electrolyte's dissociation. A strong electrolyte dissociates to completion. So that arrow is going to show the progress of the reaction going from left to right. It is a one-sided arrow, as we have always seen when we talk about chemical reactions. But in the case of a weak electrolyte, we see a double-sided arrow. That double-sided arrow refers to a set of circumstances that we refer to as chemical equilibrium. Chemical equilibrium speaks to where a reaction goes both forward and backward. So while we do see acetic acid dissociating, breaking apart in order to form H plus and the acetate anion, we can also see those anions, the H plus and the acetate anion recombining in order to form acetic acid. Well, how do we know whether or not an ionic compound will dissolve in water? How do we know if an ionic compound will dissociate, break apart into ions? Not all ionic compounds will do so. There's a list or a set of rules that's going to give us an explanation, or at least a sense of what will dissolve and what won't dissolve. For example, sodium chloride will dissolve in water, but silver chloride will not. Barium nitrate will dissolve in water, but barium sulfate will not. So, how do we determine what will and what will not? I guess we need to learn the rules. And without any further ado, all nitrates, acetates, perchlorates, ammonium salts, and group 1 metal salts are soluble in water. There are no notable exceptions. It's at this point where I really hope that you learned those polyatomic ions that I asked you to learn. All nitrates are soluble in water. All ammonium salts are soluble in water. That means that when you place any of these compounds in water, they are going to dissolve, and as an ionic compound dissolves, it dissociates. So, is lithium nitrate soluble in water? Yes, because it is a nitrate. Is calcium perchlorate soluble in water? Yes, because it is a perchlorate. Is sodium sulfite soluble in water? Well, there don't appear to be any rules regarding sulfites. But sodium sulfite would suggest that it is a sodium compound, sodium being one of those group 1 metals. things like lithium, sodium, potassium, cesium, rubidium, and francium. So sodium sulfite would be soluble in water, as would potassium permanganate. All right. Most chlorides, bromides, and iodides are soluble in water. Most of these compounds are soluble in water. Two things that I want to note. Number one, that rule does not refer to fluorides. Nowhere in this second rule do you see the word fluoride. Fluorides are not included in this rule. Simply chlorides, bromides, and iodides. And secondly, there are exceptions to the rule. When the chloride, bromide, and iodide are combined with silver or mercury or lead in the form of the lead plus 2 cation, these compounds are not soluble. Right? So, is potassium bromide soluble in water? Yes, it is a bromide. Is calcium iodide soluble in water? Yes, it is an iodide. Is silver chloride soluble in water? No. While it is a chloride, it is a silver salt, and a silver salt of chloride, bromide, or iodide will not be soluble in water. Silver chloride is a compound that historically has found great uses in the world of photography, as is silver bromide. The next rule, most sulfates are soluble in water. Most sulfates are soluble in water. Now, again, there are exceptions to the rule. And you'll note that these exceptions are not necessarily the same exceptions as we see to rule number 2. Sulfates are soluble, except when it's lead sulfate, barium sulfate, strontium sulfate, and mercury sulfate in the form of that Hg2 plus 2 cation. So most sulfates are soluble except for those 4 exceptions. Lastly, most carbonates, hydroxides, phosphates, and sulfides are insoluble. That means that they will not dissolve in water. Exceptions to the rule when these are in combination with ammonium or group 1 metal salts. And that simply just refers back to rule number 1, where we see all ammonium salts and all group 1 metal salts are soluble. So you'll see in black, we see the things that are soluble, and in red, we see the things that are not soluble. So let's put our understanding to the test. Here we have 9 compounds. My question to you is, are these compounds soluble in water? If placed in water, will these compounds dissolve in water? Once again, this would be a really good time to learn those polyatomic ions if we haven't already. I will name these compounds just for the sake of naming them. From left to right, we see potassium carbonate, magnesium sulfate, sodium acetate, iron 2 hydroxide, barium sulfate, calcium perchlorate, silver nitrate, barium chloride, and potassium nitrite. I'll give you a few moments, not too many moments, but a few moments. And here's a hint. 7 of these are soluble in water, while 2 of them are not. On your mark, get set, go, and here we go. It turns out that iron hydroxide, specifically iron 2 hydroxide, and barium sulfate are the 2 compounds that are not soluble in water. I could go through compound by compound and indicate which rule suggests that each of the other compounds would be and why these two compounds would not be. So please allow me to do so. Potassium carbonate. Well, carbonates don't tend to be soluble, but this is a group 1 metal salt. This is a potassium salt, so potassium carbonate will dissolve in water. Magnesium sulfate. It's a sulfate, and most sulfates will dissolve. This isn't an exception to the rule. Sodium acetate. It's a sodium salt. It's an acetate. They're built to dissociate. All right. Iron 2 hydroxide. Well, hydroxides typically do not dissociate, and this is not an exception. Barium sulfate. Well, sulfates do tend to dissociate, but barium is an exception to that rule. So barium sulfate would not be soluble. It would not dissociate. Calcium perchlorate, well, perchlorates will dissociate, they will dissolve. Silver nitrate, silver is not an exception to the nitrate rule. There are no exceptions to the nitrate rule. All nitrates are soluble in water. Barium chloride, chlorides will dissolve, except for a few exceptions, and barium is not one of them. And potassium nitrite. Once again, there is no rule for nitrites, but there is a rule for potassium salts. And so we see that potassium, as a group 1 metal, will allow this to dissociate. Now we need an understanding of what substances will and will not dissolve in water in order to discuss one of the 3 common types of reactions that take place in aqueous solutions. The first reaction that we're going to speak of is a precipitation reaction. A precipitation reaction is one that results in the formation of an insoluble compound, a compound that will not dissolve in water, when we mix solutions of 2 ionic compounds that will dissolve in water. Now, that may be a little convoluted, so let me break it down once again. If you have 2 solutions with soluble ionic compounds dissolved in water, if you mix those 2 solutions together and you form a solid compound that will not dissolve in water, then that is a precipitation reaction. That insoluble compound, that solid that is formed, is called a precipitant. Well, how do we know if a precipitate will form when mixing solutions containing soluble salts? I'll give you a hint. Those rules. Well, when determining whether or not a precipitation reaction will occur, we need to take note of the ions that are in each solution. So once we note the ions in solution, when we combine those ions by mixing the solutions, we have to think of all of the possible combinations. Can we see the cation of one compound combining with the anion of another compound to form an insoluble compound? So let's look at the listed equation below. Magnesium nitrate will dissolve in water. It's a nitrate. Sodium hydroxide will dissolve in water. It is a sodium salt. So if I were to mix a solution of magnesium nitrate and a solution of sodium hydroxide, the question is, would we see the formation of an insoluble compound? Well, at the heart of it all, we need to see if these compounds are willing and able to swap ionic dance partners, if you will. Magnesium nitrate is going to break apart into magnesium cation and nitrate anions. Sodium hydroxide is going to break apart into a sodium cation and a hydroxide anion. So the question is, when you take the sodium cation and interact it with the nitrate anion, will they form an insoluble compound? Is sodium nitrate soluble in water? Well, yes, it is, because all nitrates are soluble in water and all sodium salts are soluble in water. So when they combine, they're simply going to form sodium nitrate, which will dissolve in water. But when the magnesium cation interacts with the hydroxide anion, they're going to form magnesium hydroxide. And magnesium hydroxide is not soluble in water because hydroxides tend not to be soluble, with a few exceptions, and this isn't one of them. So we indicate that in the equation by saying that it will exist as an insoluble solid we see as a product of the reaction on the right-hand side, suggesting that this is indeed a precipitation reaction. So just refreshing us, if we want to determine whether a reaction is a precipitation reaction or not, we have to ask, will an insoluble compound be formed if two ionic compounds dissolved in water are able to switch ionic partners? So here are two more examples. Do these two equations represent precipitation reactions? The first one involving the combination of magnesium nitrate and calcium sulfate in order to form magnesium sulfate and calcium nitrate. The latter involving the combination of barium chloride and silver sulfate in order to form barium sulfate and silver chloride. Now we're operating under the assumption that the reactants in each case are both in aqueous solution. The question is, are all of the products aqueous? If so, then we do not have a precipitation reaction. If not, if we in fact see the formation of an insoluble compound, then that is indeed a precipitation reaction. So it would appear that the first reaction does not represent a precipitation reaction. Why? Because the products of the reaction, if those ionic compounds swap dance partners, we're going to see the formation of magnesium sulfate and calcium nitrate, both of which are soluble in water. So what happens when you mix a solution of magnesium nitrate with a solution of calcium sulfate? All of those ions break apart into solution. They form those compounds on the right, which fall back apart into those ions in solution. So we end up with just a bunch of ions in solution. But in the case of the second equation, barium chloride is soluble in water, as is silver sulfate, but they combine to form not one, but two insoluble compounds as a result of the swapping of dance partners. Barium sulfate is an exception to the sulfate rule. Silver chloride is an exception to the chloride rule. So by mixing barium chloride and silver sulfate, we see the formation of two precipitates, or what we would call a mixed precipitate. So yes, indeed, this is a precipitation reaction. Now, once you have determined whether a reaction is or isn't a precipitation reaction, you're going to have the task of balancing that equation. So, as always, there are steps to getting that job done. First of all, use the chemical formulas of the reactants in order to determine which ions are present. Write the formulas for the products, the cation from one reactant with the anion of the other, and make sure that you use the proper charges in order to write the proper subscripts. Check your solubility rules, make sure that things are soluble or are not soluble. If they are not soluble, then you see a precipitate formed. And then lastly, balance the equation. So you write down the formulas of the components as reactants. You predict the products based on the swapping of those dance partners, but taking into account the charges have to balance out. And then determining whether or not a precipitate is formed. Now, there are several ways in order to write an equation for a reaction that takes place in solution. There's your typical molecular equation, the chemical equation as we have shown in the past. But there are two other ways that may give us a little more insight as to what's taking place in solution. The complete ionic equation, as well as the net ionic equation. The molecular equation or the chemical equation lists the reactants, the products, the direction of the reaction, but it does not indicate the ionic nature of the compounds. We're simply given the state of matter in which the substances can be found. This is no different than any other chemical equation that we've encountered up to this point. But in the complete ionic equation, we more accurately see a reflection of what is actually in the reaction mixture. To say that you've got a solution of sodium chloride is one thing, but a more accurate representation would be that you have a solution of sodium cations and chloride anions. Since sodium chloride is a strong electrolyte, it will completely dissociate in solution. So potassium nitrate will completely dissociate in solution. So if I have a solution of potassium nitrate, I really have a solution of potassium cations and nitrate anions. So reflecting the reaction of potassium iodide with lead to nitrate, we see on the previous slide, we saw the basic chemical equation. But here we see what happens when those things actually break down in solution and react in order to form, as we see on the right, lead to iodide, as well as the ions that exist after the reaction has taken place. So this gives a more accurate reflection of everything that's going on in solution. But not everything that's going on in solution is participating in the chemical reaction. So therefore, we introduce the net ionic equation. The net ionic equation basically gets down to brass tacks. It says this is the reaction that's happening. Forget all of the extra, forget all the hoopla, this is actually what's taking place. In order to form the net ionic equation from the complete ionic equation, we're going to cross out any ions that appear on the left-hand side of the equation that also appear on the right-hand side of the equation in the same form. So if we look at the complete ionic equation for this reaction, we see on the left-hand side of the equation 2 nitrate anions. We see on the right-hand side of the equation 2 nitrate anions. Similarly, we see 2 potassium cations on the left and 2 potassium cations on the right. If they were to combine, they would form potassium nitrate, which is soluble in water, which would just break apart. So it's found in aqueous solution. So they exist before the reaction takes place in the same form that they exist after the reaction takes place. So they technically do not participate in the reaction. They're kind of sitting on the sidelines. It's for this reason that we refer to these types of ions as spectator ions. And as you've seen, I've crossed out the spectator ions, simply leaving the components of the reaction that actually combine and participate in the reaction. The remaining ions that form the product, this gives the net ionic equation. What happens when you mix a solution of lead nitrate with a solution of potassium iodide? The lead cation interacts with the iodide anion in order to form lead-2 iodide. Now, how do we write a net ionic equation? Well, first and foremost, we have to have a balanced molecular equation for a particular reaction. We then convert that molecular equation into a complete ionic equation by showing which things dissociate into ions. Lastly, we're going to identify any spectator ions and remove them, resulting in the formation of our net ionic equation.